So our first speaker this afternoon or in this session is Pablo Bustillo Vazquez, and his title is The Grothendieck Construction in the Lax Setting of Bicategory Theory.
Hi, everyone. So I'll speak about the lax Grothendieck construction in bicategory theory. And this work has been supervised by Dorette Planck and Martin Zill. So thank you to you both. First, I'll speak about some famous results from category theory. And actually, the first result is probably more from set theory. So if you have an index family of sets, you can compute its colimits by simply taking the disjoint union. And you can actually do something very similar in dimension one in ordinary category theory. So if you have an index family of categories, so that would be a pseudo functor from C, a category, to cat, you can construct what is a sort of disjoint union, which is the Grothendieck construction. And similarly, the Grothendieck construction is immediately a lax colimit of this diagram. And you can also compute pseudo colimits by simply localizing at the Cartesian arrows. So in dimension two, we also have a Grothendieck construction that's been introduced in 2013 by Buckley. And in this small poster presentation, we'll show that it's also a form of tri-colimits. And by doing so, we'll lay out a sort of methods that can be used to compute colimits in higher dimensions. So first, let's start by showing Buckley's results. So Buckley's construction is three-dimensional. It takes some three-dimensional data and makes it into some two-dimensional data that lives within bicats. And similarly to the result we have in dimension one, we have that Buckley's construction can be restricted to a tri-equivalence if you restrict the codomain to what I call here a cofib. So that would be the tri-category of cofibrations and co-Cartesian functors between them. And so similarly in dimension one, you have that the Grothendieck construction gives you an equivalence between pseudo functors on one side and the fibrations on the other side. And there is maybe a slightly less famous fact from dimension one is that you can actually take this equivalence and push it a little bit further into a lax setting by taking the domain and the codomain and both make them slightly bigger. So what happens here is that if you want to do the same thing, you can realize that some of the 2 cells and 3 cells used in Buckley's construction are equivalences by definition, but don't really need to be equivalences. It doesn't really invert them. And so you can drop those assumptions and try to get the most out of this construction by taking the biggest notions of functors and natural transformation that would still give you the same construction. And so you can sort of reverse engineer the definition of lax functors and lax natural transformations from them, pretty similar to those introduced by Gordon, Power, and Street in '95 and later worked on by Gursky. And so what happens is that you get what we call a lax Grothendieck construction, and you still have that it's a local biequivalence, but this time instead of going into a cofib, you get into the whole tri-category, which is bcat over b. And this local biequivalence worked in particular when G here is a tri-homomorphism. And so now we're getting very close from actually showing that the Grothendieck construction is a colimit. And we just need some very simple key observation. That is, I say very simple because it makes a lot of sense when you see the Grothendieck construction as a generalization of the disjoint union. So here, delta x is the constant functor at x. So I'm taking a constant family and saying that if you take the disjoint union of a constant family, you just do the same thing as multiplying by the indexing. So that's something you could expect, and that's something that is true. And now if you just plug into the local biequivalence that we have above, G equal delta x, you immediately get that the Grothendieck construction is indeed a lax tri-colimit. And so that's an interesting result, the linking of the Grothendieck construction in dimension two to lax tri-colimit, but you can actually push it a little bit further. And one first thing is that combining this key observation with actually just Buckley's results allows you to introduce some conical tri-colimits. So if you, once again, take G equal delta x in Buckley's result, you would say that the co-cones on F, a diagram F, are the same thing as co-Cartesian functor from the construction to B times X, which are the same thing as functors from the Grothendieck construction to X that sends co-Cartesian 1 and 2 cells to equivalences. And so this tells you immediately that if you can localize the Grothendieck construction at the co-Cartesian 1 cells and 2 cells, then you have the conical tricolimits. But now anyone has a little bit of experience with colimits in a higher dimension knows that lax colimits or conical colimits are not necessarily enough, and you need something a little bit more powerful. And so we introduce a situation that's just in between the two, which we call sigma colimits, and that's inspired by some ideas from Scott de Berg and Ziltz. And the idea is that if you have a diagram, so if you have a shape of diagram that is a bicategory B in this case, and you look at a cocone, a lax cocone on it, then basically every arrow and every 2 cell of this diagram will correspond to some data in the cocone. And if you ask for all these data to be equivalences, then this is the same thing as asking for the cocone to be weak or to be conical. And if you ask for none of them to be equivalences, you get the situation of a lax cocone. Well, the idea of sigma is to choose a distinguished family of arrows and a distinguished family of 2 cells here in this bicategory B, and to ask for the data.
It looks like you've frozen. He's back.
Oh, sorry.
No problem.
Yeah, my screen froze. Sorry. And so what I wanted to say is that if you can also try to compute weighted colimits with this technique, with this key observation, you just need to slightly change the observation. And if you look at the functor, which is bicat fx described here, then its construction is actually a lax comma. And just using Buckley's result, we can show that any weighted tricolimits in bicat will become a sigma tricolimit. So this, in a way, this method also justifies the idea that sigma tricolimits are enough to compute any forms of tricolimits indexed by bicat. And now I just wanted to speak a little bit about future possible ID to explore. And so first, most of the formulas we've shown use localizations of bicategories, which is a slightly a problem because localizations in general can be very ill-behaved. And so it's a very natural idea to ask yourself, can I take some assumptions on my diagram to have an easier localization to work with? And so a common idea would be to look at the calculus of fraction as developed by Planck in 1996. And this exactly gives you the ability to compute any filtered conical tricolimits in bicats. But there's something that's not completely satisfying with this approach, is that the localizations we had in the formulas before were localizations at 1 cells and 2 cells simultaneously. And so what one could try and do is to invent a notion of calculus of fraction, of bicategorical calculus of fraction that would use 1 cells and 2 cells at the same time. Such a notion could lead to another notion of filteredness, to still have a statement saying that sigma filtered, a sigma tricolimit could be computed by calculus of fraction. So here you would try to generalize ID from the paper I cited before. And by taking a bicategory B in some distinguished family of arrows and 2 cells and asking for some axioms that look like the filterness axiom, and that would allow you to compute any sigma tricolimit of this shape using a calculus of fraction that we just defined, and maybe with the additional property that those would exactly correspond to the colimit commuting with finite weighted colimit in brackets, finite weighted limits, sorry. And so overall, if there is one thing to keep in mind from this presentation, is that we laid out sort of a technique that is already a little bit known in dimension 1 and 0 to compute colimits. But this technique generalizes very easily to higher dimensions, and also gives you the power to compute, to justify the idea that sigma colimits are enough, and that any weighted colimit can be transformed into a sigma colimit. And something else curious about this work is that we used the Grothendieck construction to actually guess the definitions of lax functors and lax natural transformation it's only using a definition of dimension 2. And this is because the Grothendieck construction has, in and out of itself, a dimensional shift that allows you to compare things from different dimensions. And this is interesting as it is, well, complicated to understand definitions in higher dimensions. So linking them is always helpful. And also, there is something curious is that this method gave us a definition of Lax functor and of Lax natural transformation simultaneously. And so it's sort of interesting because there is always this small debate about should we call them Lax, Colax, Uplax. And here we have a way to create them both at the same time. So maybe we should give them the same name. And so that's all I wanted to say. And those are the references. And thank you for listening. And I think we have some time for questions.
Yes, are there any questions or comments?
I'll show the poster that will be on the forum.